This is a medical resource allocation system designed using machine learning based on predictive disaster data, primarily focusing on the allocation of medical personnel and ambulances. Next, I will demonstrate the system's complete workflow. Data collection for the system utilizes the IFRC API interface to obtain global disaster data spanning the past 5 years. This primarily includes disaster event data, field reports, medical units, countries, regions, districts, local unit options, and disaster types. Finally, predicted disaster events data is acquired through IFRC's RiskWatch and GDACS. All raw data is stored in the data raw directory, categorized by data source, and saved in JSON format to ensure data integrity. The preprocessing stage primarily involves preparing 3 datasets: historical disaster events, forecasted disaster events, and public local unit data. This process focuses on identifying and handling missing values, outliers, and duplicate records to ensure data quality. Categorical encoding converts textual variables, such as disaster types and medical specialties, into numerical codes for algorithmic processing. Preprocessing occurs in 2 stages, with intermediate results stored in the data interim directory and finalized standardized data in the data process directory. Event features primarily extract key metrics, including quantified disaster severity, predicted duration, and calculated spatial impact range. Most critically, paired feature generation constructs an efficient spatial indexing system. The Haversine formula calculates geographic distances between events and medical units, while priority scores are computed based on urgency levels and resource matching factors. This feature engineering approach translates complex geospatial relationships into computable numerical features, providing high-quality input for subsequent machine learning models. Feature data is stored in the data features directory. This system primarily compares 3 distinct machine learning models for addressing resource demand forecasting. The baseline model employs ridge regression to establish a performance benchmark, delivering stable and reliable predictions. The random forest model automatically handles nonlinear relationships and complex interactions among features, making it particularly well-suited for our multidimensional heterogeneous data. As a deep learning approach, the ANN model utilizes a multi-layer perceptron architecture to capture deep, intricate patterns within the data. Model stability is evaluated using k-fold cross-validation. During training, hyperparameters were optimized using a combination of grid search and random search. All trained models are stored in the models directory. To select the optimal training model, the system primarily employs multiple complementary evaluation metrics: mean squared error, real mean squared error, and R-squared. Additionally, the system implements an automated model selection mechanism that automatically chooses the best model based on comprehensive performance indicators, enabling intuitive comparisons of different models' performance across metrics. All evaluation results and performance reports are stored in the model's production directory. The system infers the number of affected individuals assigned to each unit based on the selected optimal model, storing data in models predictions. Subsequently, it configures medical resource mapping parameters according to humanitarian response guidelines to forecast medical resource needs and unit allocation plans. Data is stored in models predictions allocation. To enhance the system's practicality, an intuitive and user-friendly web interface has been developed. Running the run web coding file, the simple website is displayed. The homepage displays an overview of predicted disaster events, allowing users to browse basic information on different events. The allocation details page provides a comprehensive resource allocation plan for each event, including the required number of medical personnel and ambulances, along with the specific allocation quantities for each unit type assigned to the event. Since a predicted disaster event may involve multiple units, this page primarily displays allocation data for the top 2 significant units. The remaining unit-specific allocation data for each category is represented by other.